Model ships are made for navel gazing. They're representations of real ships. Some are built meticulously to scale with extreme attention to detail and are truly museum pieces. You can buy model ships pre-assembled or in kits. But be careful, these are truly delicate works of art. The Portland steamer sank in the Atlantic in 1898, all lives lost. But its image survives in models. To make a model like the Portland, the worker selects some wooden pieces from a stockroom. Model ships are actually made of thousands of parts, big and small. These are just a few, and some are to be cut down. A computer guides a laser beam as it carves the larger flat pieces of wood into many parts. They'll be components for the ship's deckhouse. Next, a worker shapes a hull or main body using a machine called a duplicating carver. Holding the machine's stylus on the left, he traces around a master shape. This motion guides two routers on the right as they chisel into basswood, making exact copies of the master hull. To make resin parts, they mix polyurethane with some plasticizer and pour it into a mold. A chemical reaction causes it to harden. This takes up to a half hour, and then they pull a newly shaped lifeboat out of the mold. Next, a worker cleans up another mold. It's to be used to shape cast metal anchors. He places the mold in a centrifuge and pours a melted mix of tin, antimony, and copper into it. The centrifuge spins, and this causes the metal to fill the cavities in the mold and solidify. He opens the mold and finds the anchors form like spokes around a hub. It's anchors away as he snips them free. Now, a worker sands smooth the bottom of the hull. Then he positions the first of the ship's 5 decks. He glues wooden spacers between the decks. A special glue that dries in about 10 seconds allows him to work quickly as he builds the tiers. Next, he submerges a deckhouse side piece in water to soften the wood. He cuts the little tabs to free other deckhouse parts from a matrix. After that, he carves out the center of 2 of the pieces. Then he glues a block between them and applies more glue to the edges. He bends the deckhouse side, which is now wet and supple, around the structure. The moisture causes a chemical reaction in the glue, which strengthens it. After he positions the deckhouse starboard side, he sticks a strip of clear acetate to the back of a band of windows. The acetate simulates glass. He paints the front of the windowed wall white, and then turns it around to paint red curtains on the acetate. Other detailing has been laser etched into the wood. He glues the wall of windows between deck tiers, and the look is authentic. He positions paddle wheels on each side. These have 57 wood paddles held in place by brass radials. Remember the anchors cast in the centrifuge mold earlier? He now positions some on the ship deck. Then he prepares the lifeboats. The larger plastic one goes on the upper deck. This golden eagle is the finishing touch. Here, another worker rigs up a 4-masted schooner. Using surgical clamps, he pins the ropes down so they don't get in the way. Then he measures a piece of decking to make the top of the deckhouse. He glues it to a base and then positions it on the ship. Next, a jeweler's lathe spins a piece of brass as a worker manipulates a cutter, milling parts for the ship's bell. Once it's mounted, this ship model is ready for everyone to admire. The V-twin motorcycle engine actually dates back more than a century. Talk about staying power. Central to the design are two cylinders that form a V around the crankshaft. This configuration is more compact than a straight-line engine, and its appeal is timeless. With its throttle cranked, the V-twin can take you on an exciting ride and leave sedans in its dust. To make one, a robot loads a cylinder into a machine equipped with cutting tools. The tools mill the cylinder's metal slats to highlight them. The slats are called cooling fins. They allow the engine's heat to dissipate. This cutting tool bores into the center of the cylinder, carving it to precise dimensions to allow engine components a perfect fit. Next, an operator assembles the crankshaft. He aligns connecting rods and slides them over bearings. He then assembles the rods and bearings to the crankshaft. A machine press fits everything together. Next, a lift scoops up the crankshaft assembly and transfers it to the lower half of the crankcase. At the next station, an automated dispenser precisely applies sealant to the inner edge of the crankcase. They then arrange the upper half of the crankcase on the lower assembly and bolt the two together. It's now time to link the crankcase and shaft assembly to the transmission. This chrome-plated cover is the finishing touch. Next, they fit the camshaft into the crankcase. Its job is to maintain valve timing. They position the pistons on the connecting rods, now installed in the crankcase. Remember those highlighted cylinders made earlier? Workers now slide them over the pistons. These are the cylinder head castings. Technicians paint them and then machine them to fit on the cylinders. A robot bolts them together with just the right amount of torque. The operator then installs tubing that will house push rods. He snaps them into the cylinder heads. Then he clips on metal covers to secure them. He now inserts the push rods in the tubing. Up next is the electronic fuel injection system, which controls the flow of fuel to the engine. They install it between the two cylinders. A special bracket holds the injection system in place. He bolts the rocker boxes to the cylinder heads, then tops off the assembly with more gleaming chrome covers. The operator now screws the oil filter onto the engine case and secures it with a special wrench. This is the electrical charging system. It goes on the crankshaft. Now it's time to pump oil into this V-twin engine and put it through its paces. Computerized testing equipment moves in and mates to the engine. The engine rotates and they shift the transmission through all the gears. This allows the testing equipment to analyze every aspect of its performance. Next, they insert spark plugs into the cylinder heads. And these 1584cc motorcycle engines are now revved and ready for their wheels. The invention of the motorcycle late in the 19th century was speed-driven. People wanted to go places faster than they could on a bicycle, so they strapped an engine on a bike, a simple concept. Today's motorbike is much more complex, and it leaves the earlier versions in the dust. These motorbikes are an engineering feat. They start by welding the frame out of lightweight aluminum, an advantage for speed and fuel efficiency. The frames are cleaned, powder painted, then baked to cure the paint. They fit a crankshaft and pistons into the engine's left block. They tighten the bearings and caps, then slide in a U-shaped tool called a fork that orients the pistons in an upright position. Next, they compress the piston rings with another tool so that the pistons easily slide into place as they install the other half of the engine block. They place a gasket on the top of the block and then install the cylinder head. Using torque-controlled electric tools, they tighten the bolts to attach the cylinder head to the block assembly. They install the camshaft in the cylinder head unit. The camshaft will drive the valves that bring in air and fuel and let out the exhaust. They rotate the crankshaft to fine-tune its action. Now it's time to give this engine a little test run. They fill the engine with coolant and fuel, then run through the gears. They check for leaks and overall function. When it passes inspection, they purge the coolant from the engine. A motorbike engine isn't only about function, it also has to look good, because it won't be totally hidden under a hood. Now, they lower the 225-pound engine onto a cradle that sits on a conveyor. They mount the frame onto it. They attach the rear wheel assembly, and then the front wheel. They attach the handlebar using torque-controlled tools. And they tighten the brake assemblies. Next, they fill the radiator with antifreeze. Meanwhile, over in the paint department, robots are hard at work. They attach the painted pieces to the bike. First, the saddlebag body, then the lid, and finally the trunk body. Then they assemble the instrumentation. The speedometer, fuel gauges, and many other things all go into one unit. This part is called the front cowl, and it goes right in front of the instrumentation. They lower the front cowl with a meter panel onto the bike. And then they bolt everything to the frame. Finally, they install a cover for the exhaust pipe. They check everything to make sure it's solidly put together. And then they pull up to a dynamometer, a machine that measures mechanical power. They check the bike's speed, brakes, horn, navigation system, and the cruise control. Every motorbike undergoes this scrutiny, and if it passes, it's ready for life on the road. If you've ever had to stop suddenly while driving at high speed, you know that once you hit the brakes, they can easily lock up, making you skid. But with the sophisticated computer technology behind today's anti-lock brakes, skidding is becoming a thing of the past. Brakes are absolutely essential equipment for every vehicle to slow down and stop. And brakes have remained practically unchanged for the past 40 years. Conventional disc brakes have pads that press against the brake disc, attached to the wheel. These pads grip the disc on only 15 to 30 degrees of its circumference. This develops high heat, wheel skidding, and results in premature wear. The new floating disc brakes have two pads of friction material on 360 degrees of the disc. When the brake is applied, hydraulic pressure activates the diaphragm, which applies pressure on the inboard pad, which is then pressed against the disc. In this animation, the diaphragm movement is exaggerated. However simple, the design of this brake calls for some complex development steps. It all starts on the monitor screen with computer-aided design. This powerful software creates objects in 3 dimensions, which can be virtually manipulated. They then proceed to digital analysis. Here, digital models are submitted to repeated braking to verify that the parts conform to design objectives. The software verifies changes in heat, the effects of vibration, and resistance to breakage. The right choice of materials is critical. The electrical components also have to be created. Here we see the delicate construction of tiny sensors that measure the force exerted by the braking system. The sensor is the main component of the intelligent ABS braking system, which functions more efficiently than traditional anti-skid systems and reduces braking distance. Next, it's the fabrication stage of prototype parts which will be tested. The machining of these parts must take into account the requirements of mass production. This high-precision robotic machining is done by computer-controlled digital machines. A liquid sprinkled on the machine part cools it during the process. The finished parts are precisely measured, then fitted and assembled to form the total braking system, which will be first tested in the laboratory. Brakes in full contact have a friction surface 6 times superior to traditional brakes. The use of aluminum and composite materials allows for a weight savings of 5.5 pounds per wheel. This affects road holding and reduces fuel consumption by 0.05 gallons per 100 miles. They proceed to power and endurance tests on this dynamometer, in which a brake and wheel assembly act against a large rotating drum. These lab tests are critical since they can detect any defect in a braking system before it's installed on an actual vehicle. In order to evaluate the power and endurance of the brakes in full application under extreme conditions, they were installed on this Porsche 911 Turbo, entered in the Motorola Cup. They proved completely satisfactory, and the Porsche went on to record many wins. Once all validation tests are done, we move on to the next step. Brakes are installed on a production model vehicle. With data systems, engineers can observe the performance of brakes under all conditions, thousands of times a second. Finally, engineers proceed with actual braking trials with test vehicles. All that remains is to produce brakes on a large scale to supply auto manufacturers' production lines. And that's the story of brakes, from original idea to final product. Changing your car's oil filter a couple of times a year is an easy way to prolong the life of your engine. The oil pump forces oil through the filter to the moving parts in the engine. The filter's job is to block dirt and metal debris from getting in between those parts and causing engine damage. They make many oil filter parts from steel coil, a sheet of steel on a roll. They start by unwinding the roll and feeding the coil into a press. The press contains a series of dies, each of which progressively stamps the steel into the shape of the specific part they're making. This press is churning out tapping plates, a component on the end of the oil filter that screws onto the car's engine. Hot off the press, the tapping plates travel on a magnetic conveyor to the welding station. There, a robotic arm loads them onto the welding carousel. But before any welding begins, a nozzle applies sealant around the rim of each plate. This will fill any gaps left between the parts after welding. A robot now welds the tapping plate to another steel part called the bottom ring. This ring will hold the gasket, the rubber seal that prevents oil from leaking out as it travels through the filter into the engine. The welded parts, known as the bottom assembly, now go into a machine that cuts a thread pattern through the center. This will enable the oil filter to be screwed on to the engine. Another press produces the oil filter steel body called the canister. The dies first stamp out a rough canister shape. Then they reduce the diameter and make the can taller. Finally, they cut off the excess. Elsewhere in the factory, another machine cuts and perforates pieces of tin-plated steel coil and rolls them into tubes. We'll see where those tubes go shortly. Yet another machine prepares the filter's key component, a filter paper that works like a fine sieve, trapping dirt, carbon, and soot. First, the machine pleats the paper so it will fit inside the canister. Next, the machine cuts the continuous ribbon of pleated paper into lengths. It folds each piece into a circle, fastening the ends with the steel clip. The next machine assembles what's called the filter cartridge. It places each filter paper over a tube. The tube's job is to reinforce the paper against the force of the oil pumping through it. This machine glues a capping disc on each end of the filter paper to hold the tube in place. A heater cures the glue. Now for the final assembly. As the canisters go by upside down, automated arms insert the filter cartridges. A worker then puts a thin rubber disc on top of each cartridge. This disc will prevent the oil from draining out of the filter. Now for those bottom assemblies we saw them making earlier. A worker positions one on each canister. Then a machine called a seamer folds its edge down, forming a rim, just like the rim of a soup can. Now the conveyor turns the filters right side up as they file by 5 nozzles spraying powder paint. An infrared oven dries the paint in about 90 seconds. Then a printing machine stamps on the product information. The conveyor now turns the filters upside down again as they travel to the gasket inserter. Its automated plungers insert a gasket into each bottom ring. These automotive oil filters are finally finished and ready to do the dirty work.